In this video, I'm going to go over the time library in C, which includes functionalities for accessing the current time and working with times. So to use the library, we're going to include time.h, and time.h comes with C, so you're always going to have access to it. And then we'll just run through the functions in this library one at a time here. So I'm going to call here time with the argument null. And what this function does is it returns the current time. Now we're going to store that time that it returns with this special variable type here. So time underscore t, and we'll make a variable called now. So time underscore t, that's a special variable type that comes with the time library. And it's basically a synonym for a long integer, a big integer. And that's what time is going to return when we call it with the argument null. So we could print it out just to see what it looks like. We'll say printf %ld/n will output now here, just to see what it looks like. And then we'll do a compilation and we run it and we get this big integer here. Now, if I wait a few seconds and run it again, it's been incremented by a few seconds. If I wait, a few more seconds and run it again, it's going to be incremented by a few more seconds here. So what's going on here is that this function actually returns the number of seconds since January 1st, 1970 at midnight. And that's just called the epoch. It's sort of when we start counting from. And this function returns the number of seconds since that time, since that point in time. And what we could do is we could actually then do something like sleep our program or run some computations for a certain amount of time. And if we call the time function again, we'll have seen that the time is actually incremented. So let's do that. Let's actually include uni_std.h because this includes the sleep function. The sleep function will actually just put our program to sleep for a couple seconds, whatever time we specify. So I could say here sleep 2, and this will put the program to sleep for 2 seconds. I could make a different number, but I'm going to say 2 seconds. And then what we'll do is we'll get the time again. And we're going to see that the time is actually going to be incremented then by 2 seconds. So if I say time t 2 secs, and then we do a printf here of 2 secs, we'll see that 2 seconds will have passed. So we'll say 2 secs here, and we do a recompilation here, and then run it. And we get a number that's 2 bigger than this number, right? If we run it again, same thing. The number is going to be, 2 bigger than this number. And what's going on there is that we're pausing our program's execution for 2 seconds with this sleep function. And then when we get the time again, the time's been altered by 2 seconds, right? It's been increased by 2 seconds because 2 seconds have passed. And so this is how we can work with time in our C program. It's one of the ways we can work with time in our C program. There's actually a function that gives you the difference of 2 times. So we could call diff time, and diff time is also provided by time.h, and it gives you the difference between 2 times. So I could say diff time 2 seconds, and I could say now, and it'll return a double value. So I could say here double diff is equal to diff time, and then I'll do a printf here. I'll just printf diff. So print out diff, and we should see that 2 seconds have passed. So if I do a clear recompilation and run it, we get the 2-second pause, and diff is going to be 2. Now, we might not know what the difference is going to be because maybe our program's done some computation. So instead of sleeping for 2 seconds, our program does a whole bunch of work. And then we get the time again, and when we do the difference, we don't really know what the difference is going to be. But in this case, we know it's going to be 2 seconds because we slept for 2 seconds, and so that makes sense. So that's that. I mean, there's a bunch of functionalities for working with time, though. One of the things that's kind of annoying with what we've got right now is that this is not a super useful format for time, right? Like this big, long number here. If somebody asks you what time it is, you wouldn't give this number like 162828. That's not how humans read time, right? So one of the functionalities allows us to get a nice, pretty string of the current time. And that function is called ctime. So ctime allows us to get a nice, pretty string of the current time. So let's actually just do that now. We'll say here car star, and then we'll say string underscore now is equal to ctime and now. So the way the function works is you pass it a pointer to a time t variable. So we're giving it, and now we're giving a pointer to this time t variable here, a memory address for a time t value. And then the function is going to return a string, and we're going to actually store it with this car star string now, and that'll be a pointer to the string that's returned. And then we could print it out. So we could say printf, and we could say here %s/n string underscore now. And we'll get this nicely formatted time here. So we get Friday, August 6th. This is the time. This is the year, and so forth, right? And this is like more human readable now. Now, really though, if we want to programmatically work with time, we'd probably want to know things like not just a string representing the entire time. We want to know things like what is the current hour, what is the day of the month, what is the current month, what is the current day of the week, and things like that. And there's actually a way of getting a struct that contains members with these individual pieces of information. And there's two functions that do that. One is called GM time, which gives you the Greenwich Mean Time. And the other one's called local time, which gives you that information for your local time zone. So we'll use the GM time function first. So we can say GM time, and you pass it and now. So you pass it again, a pointer to a time t value here. And then what it's going to return is a struct, actually a pointer to a struct. So we can say here struct tm star gm underscore time. Star gm underscore time is equal to gm time. So this is the variable name, and it's a pointer to a struct tm. And a struct tm is basically just a struct that's going to contain a breakdown of all these pieces of information that we'd want to know about a time if we want our program to work with times. And we'll just print out each one of those members separately and then go over them one at a time here. So we can say printf, and I could say here tm sec %d/n, and I'm going to say gm underscore time tm underscore sec. And that's one of those pieces of data here that's in this struct here. And it's a pointer to a struct, so that's why I'm accessing it with this dash greater than symbol here. That's the operator that allows me to access the members of a pointer to a struct. And so I'm just saying, like, go get the tm sec member of this struct here. And I could print out each one of these members here. There's actually a number of them, so it'll actually take a second to actually go through. There's minutes, there's hours, there is the day of the month that it is, there is the day of the month, M day, TM month. Oh, there's the month. This is the day of the month. This is the month. This is the year. This is the day of the week that it is. This is the day of the year that it is. And this is whether it is daylight savings time or not, is DST. And then what we could do is we could just modify these so we're just clear what we're printing out here. So we'll say TM minutes, TM hours, M day, MON, year, W day, Y day is DST. Okay, so if we do a recompilation then and run it and print it out here, we're gonna get this breakdown here. And this actually matches the data up here, really, because what you've got is like TM sec, that's the 55 seconds. TM min, 36 minutes. TM hour, 15. That's actually not gonna match in this case because we're not using our local time zone here. We're using the Greenwich Mean Time, right? So in my time zone, it's 11 o'clock. But in the Greenwich Mean Time zone, it's gonna be 3 o'clock. And so that's why that doesn't quite match there. So TM M day, that's the day of the month, which is the 6th. TM month, that's 7, which is actually August, because we start counting from January being 0, right? So January is 0, February is 1, March is 2. By the time we get to August, it's 7. TM year 121. That looks a bit funny. So the way it works is TM year is going to be the number of years since the year 1900. So because it's 2021, that's 121 years since 1900. That's why we get 121 there. So if we ever wanted to like output, say 2021, we'd have to add 1900 to this TM year value to get the current year. TMW day, that's giving you the number of days since Sunday. So because it's a Friday, you got like Sunday, Monday, Tuesday. By the time you get to Friday, it's 5. And then TMY day, that's giving you the day of the year it is. So it's the 217th day of the year. And TM is DST. This is giving you whether it's daylight savings time or not, which it's not. And so we get a 0. Now, there's another function called local time. It just gives you all this data, but for your local time zone. And I'm in the Eastern Standard Time Zone, so it'll give me the data relevant for that time zone. And you just call local time. You just say local time, and it gives you back the exact same sort of struct here. So I'm just gonna say here cur underscore time. I'll call it cur time. It gives you back the exact same struct of data. It's just that it's now for your time zone. So instead of like GM time, I'm gonna say cur time now. And we'll just print it out for my time zone now. And it won't be too different. I'll just throw a new line here, just that way there's a bit of separation between these two chunks of data I'm gonna output here. So do a clear, recompile, and run it. What did I do here? TM cur time, local time. Oh, I forgot an L there. I missed an L in there. So it was loca time. So it's gotta be local time. So all right, clear that. recompile, run it. And here we get the same data, but now it's for my local time zone, right? So now like the TM hour being 11, it actually matches this data here. And so that's all good. And you've got like the year and the day of the week and all the usual stuff. And it is daylight savings time. So this is now true. And so that's, basically it there for local time. It just gives you a breakdown for your local time zone. Now, one of the things we might want to do is get another representation of the time here based on cur time. So what we could do is we could say here car star other string is equal to ASC time cur time. And then I'm gonna do a printf of this other string. So let's say printf %s other string. Do a clear, recompile, and run it. And we get the string representation. But this time it's a string representation based on this struct here. Now, the reason why I might want to do that is because maybe I actually make one of these structs myself with my own values. So like I could change what the struct is going to contain in terms of the seconds, minutes, hours. And then I could do a printf of the string that's been produced by ASC time with that struct. And I could get some printout for some other time entirely, for example. So this is another function that's going to return a string representation of the current time. But unlike working with the time underscore t type, this one is going to work with the struct tm type. But other than that, it pretty much does the same thing. So there's some other functions as well. One is mk time. And mk time, that's actually going to convert a sort of struct time like this to a time t type time. So it goes from this sort of struct type to a time underscore t type. So to do that, we'll say here cur time, and I'm going to say tm. So cur time, I'm going to say tm seconds is equal to cur time tm seconds plus 1. Then I'm going to say here time underscore t new time is equal to mk time cur time. So what I'm doing is I'm taking the current time and I'm incrementing the seconds of that time by 1. And then I'm saying time underscore t new time is equal to make mk time cur time. What this is going to do is it's going to take this struct representation and it's going to convert it back to this sort of time underscore t representation of the number of seconds since 1970, January 1st, 1970. Now if I do a printf then of new time here, %ld here, we should see that it's been incremented now by 1 since now. So we could do a printf of now as well. Say %now, %ld/n, and we'll print out now. And then we'll say new time here as well. And if we do this compilation here and run it, I get that now is this and the new time is this. And what's gone on is I've taken time that's in this sort of struct format and I've added 1 to the number of seconds. So I've added 1 to the number of seconds, right? And then what I do is I take that and I convert it back to the number of seconds since 1970, the number of seconds since January 1st, 1970 format. And when I do that conversion, we see that the new time's been incremented by that number of seconds. If I increment it by, let's say instead of incrementing the number of seconds, let's increment the number of minutes. I'll say number of minutes, tm min. Let's increment the number of minutes by 1. And then what should happen is this number should increment by 60 actually, right? Because it's 60 seconds in a minute. So I run it here and we had now as being, 594, but now I get 654, which is 60 seconds later, right? Because I incremented the current time by the minute value, the minute member, by 1. And that's going to increment the number of minutes by 1. So instead of tm min 43, it's going to be tm min 44. And when I take that time and I convert it to this time t value, that's why I get this time that's been incremented by 60 seconds now. So this allows us to convert from one time format to the other, similar to what we're doing with these sorts of functions here. To be honest with you, when we take a time representation with time t and we convert it to this struct tm type, we're doing a very similar thing, just sort of backwards here. We're converting it the other way. Another function that's interesting is the strftime function. What that does is it gives us a time in string format, but it allows us to customize using placeholders exactly what that looks like. Let's go over that function now. I'm going to say here car s100. And this is basically going to be a buffer where I'm going to store the string. So I'm going to store the string into this character right here. And then you call the function like this. You say strftime, and you give it the name of the string, the maximum number of characters to store, and then you give it the string with placeholders that specify how to format the actual data that you want. So if I say here %a, %b, %d, and then I say here cur time, what this is going to do is it's going to say, based on this time struct here, based on the struct representation of time here, format the data like this into a string. And these are placeholders for specific things. So what you actually want to do is find a resource like this online. I'm going to include a link to this one in the description for this video here. But what this does is this gives you the ability to output certain data. So like when I say %a as a placeholder, as a specifier here, what it's going to do is it's going to output the day of the week, the full weekday name, whatever that is. When I say %b, it's going to give the full month name, whatever that is. When I say here %d, it's going to give the day of the month from 01 up to 31, whatever that is. And so, and it's going to store that then into this string here. So this is basically specifying like how to format the string in terms of what data to output and in what order. And this is basically specifying the current time that should be represented in this string. And then this is then saying, okay, store it into this string here up to a maximum of that number of characters here. So if I do a printf here and I say printf %s/n and I put in s, we're going to get a string formatted as we've requested it. So if I say clear here, GCC and run it, I get Friday, August 06. And that's because %a is the day of the week, %b is the month, %d is the day of the month, right? And so that's why we get that. Now I could put this in a different order. So I could say here %a, %d, %b, and do a recompilation. And now I've got Friday, 06, August here. And I've kind of rejigged the order of things here. So what you can do is you can use these things here. You can use these specifiers here to make whatever you want in terms of the format. And they give you all kinds of options here. So it'd be quite a bit to go over all of them. So I actually just link you to this document here that'll just help you to see what's there. But basically you can then make it whatever you want. So if I want to do something like this and say, let's say %l, %p. So %l, %p, do a recompilation here and run it, I get 11 a.m. So it's giving me like the hour of the day and AM or PM. And the amount of customization you can do there is pretty big. So it's a pretty cool thing to check out. Now, one thing the function does return is the length of the string. So if I say like int strlen is equal to the result of this function call here, this will give me the length of the string here. So if I say printf %d/n strlen, it'll give me the length of the string that was just built here, not including the null terminator. So do a clear recompilation, run it, and I get 5 because you got like 1, 2, space, 4, 5, right? 1, 2, 3, 4, 5. And so that's the length of the string that it gives you back. If the string that's produced goes over this length here, it'll return 0. So if it goes beyond this length, it'll return 0. So that's the strftime function. And there's all kinds of customization you can do with it, but it's the kind of thing where you go over the placeholders here. You kind of would make it however you want for whatever you're trying to do. And you'd go through these and kind of figure out what you want based on them. So there is another function called clock, and clock gives you the current number of clocks that have elapsed. And we can use that to actually measure how long something has taken to execute in our program. So I could say here clock _t start and end, and make two variables called start and end. If I say start is equal to clock and then end is equal to clock, this is going to give me the number of clocks and the number of clocks at the point that this is called. And by clocks, we mean with our CPU. The CPU has a number of clocks per second. And what we can do is we can get the number of clocks, and it'll be the number of clock ticks that have elapsed since the program has started running. So your processor basically does a certain number of clock ticks where it's just doing some work. It's sort of getting into like a lot of hardware stuff to really get into like what that means. But basically your program is doing a certain number of ticks, a certain number of clock cycles per second. And when we say start is equal to clock here and end is equal to clock here, we're basically getting access to the number of ticks since the program has started running. And this is something we could actually use to measure performance. So what I could do is I could have some functionality in here, some work being done in here. And I'll say like I is equal to 0, I is less than some very large number here, I++. And we're just going to do some make-believe work here. Like we're not going to have the loop actually do anything, but we are going to have the loop run 0 until this very large amount of times. And we're going to get the number of clock ticks before we do this and the number of clock ticks after we do this. And this can actually be used to measure how long something took the processor to do. So we could say here like printf, and I'll say, let's print out the number of the amount of time. So I'll say printf %f /n, and we'll print out total. And then I'll get the total here. So I'll say double total is equal to double, and I'm going to say end minus start, and I'm going to do a division by clocks per second. Clocks per second. So what I'm doing here is I'm taking the end number of ticks, subtracting the start number of ticks, and that'll give me the difference in time, and I'm converting it to a double. Then I'm doing a division by clocks per second. So clocks per second is a constant that's going to be defined in time.h, and it's defining the number of clocks per second. So what I'm doing is I'm saying like, okay, get the number of clock ticks that have occurred before we do something, get the number of clock ticks that have occurred after we do something, then get the difference of those two things, right? That's giving us the number of clocks that took place while this was occurring. Then I'm doing a division by clocks per second. So take the total number of clocks that elapsed from the start to the end by doing this diff here, by doing this subtraction here, and then divide it by clocks per second. And that's going to give me the total number of seconds that has elapsed since this this work was done, right? And so if I do a printf now of time %fs here, what that's going to give me is the amount of time that's passed. So I could do a clear and a recompilation here. Oops, did I do something wrong here? End minus start. It should have really worked there. What didn't it like there? Oh, I forgot the double here. I spelled double wrong there. I think it was even telling me, look at this. It was even telling me use of undeclared identifier double. Did you mean double? So yeah, I blew it. All right, so we'll do a recompilation, run it here. And we get the time that has elapsed is 1.53 seconds. If I were to factor that down by 10, like do a delete of one of those zeros here, so it should be like 10 times faster now because it's doing 10 times less 10 times less iterations of this loop here, then it should be something like 0.153 seconds. So right here I get 0.155, right? And so what again is going on here is we're taking the number of clock ticks that have occurred since the program has started running. At this point, we're doing a bunch of work, and then we're getting the number of clock ticks that have occurred since the program since the program started running at this point, right? And when we do a subtraction of those values, we're getting the number of clock ticks that occurred while this work was being done. And then we do a division by the clocks per second. That's going to then give us this number of seconds, and it could be like a fraction of a second, but it's giving us the time in seconds as a double that this amount of work took. And then we do a printf of that amount of time here, and we get that result there. So this is actually a technique we could use to measure how long something takes to run in our program. And so that completes our run through of the essential functionalities of the time library. Check out portfoliocourses.com, where we'll help you build a portfolio that will impress employers, including courses to help you develop C programming projects.